Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So what we're going to look at today is section 3.7, which is a victory lap around chapter 3, in which we will discuss a cute schematic representation that displays all of the possibilities that we've been talking about for how these systems can turn out. And this is called the trace determinant plane. Alright, well, determinant, that's an old friend of ours. Trace, though, you might not be as familiar with. So, trace. So the trace of a matrix is equal to the sum of the entries along its main diagonal. So if A is equal to a 2 by 2, A, B, C, D, then trace of A is just equal to A plus D. So note the trace of a matrix is always the same as the sum of its eigenvalues repeated by multiplicity and the determinant is the same as the product of the eigenvalues, again repeated according to multiplicity. Alright, so that's just a note. This relies on some linear algebra stuff, so we won't really get into it right at the moment. But let's go ahead and look at the consequences of this. So then, the characteristic polynomial for a matrix A with eigenvalues lambda 1, lambda 2, and this is allowing the possibility that these are complex and allowing the possibility that they are the same. So repeated according to multiplicity can be expressed in the form, and actually here I'm going to do a quick little change here. Characteristic, not just polynomial, but characteristic equation is more helpful here. The characteristic equation, so it can be expressed in the form lambda minus lambda 1 times lambda minus lambda 2 equals 0. So this is just the natural factored form of a polynomial with with roots at lambda 1, lambda 2. And then if we FOIL it out, it would be lambda squared minus lambda 1 lambda minus lambda 2 lambda plus lambda 1 lambda 2 is equal to 0. Or in other words, lambda squared minus lambda 1 plus lambda 2 lambda plus lambda 1 lambda 2 equals 0. And what we see here is the sum of the eigenvalues and the product of the eigenvalues. And so that gives us lambda squared minus t lambda plus d, where t is equal to the trace, d is equal to the determinant. Now, then, the different scenarios that we've been discussing can be all derived from the quadratic formula applied to this. So then, we can use the quadratic formula to classify the eigenvalue possibilities. So in particular, so lambda squared minus t lambda plus d equals 0 implies that lambda is equal to t plus or minus the square root of t squared minus 4a, which is 1, times c, which is d, all divided by 2. Now, if we look at the discriminant, delta equals t squared minus 4d, this will determine the nature of the solutions that we'll find. So if delta is greater than 0, there will be two distinct real eigenvalues. If delta equals 0, one repeated eigenvalue, and if delta is less than 0, two complex eigenvalues. Now, what we can do to actually use this insight is basically take the situation here and set it equal to 0. So t squared minus 4d equals 0. So then that means that 4d equals t squared, which means that d equals 1/4 t squared. Now, if d is less than 1/4 t squared, then we look here, that means this will be positive. That means we have the two real eigenvalues. if D equals, so this is kind of like some scratch work here. So if D equals 1/4 t squared, 1 repeated eigenvalue, and if D if D is less than 1/4 t squared, complex. Eigenvalues. So then what we can do is we can actually plot the parabola on the d by t plane, and based on the region that the combination of d and t land us in, we can determine what sort of solution we would expect. So then, if we plot d equals 1/4 t squared on the dt plane, the position of a combination t comma d will indicate the nature of the solutions. So let's try this out. So we're going to make ourselves a nice big determinant trace plane, or trace determinant plane. And we're going to just look at the parabola. D equals 1/4 t squared. Okay, so let's just think about this. So if D is sorry, a second. The reason why I was hesitating there was because I just noticed a mistake there. That was supposed to have been greater than, right there, greater than, for complex. Okay, so back to work. So the reason why I hesitated was because I was about to throw into question everything I was about to say. But, so this whole region up here is the region of complex eigenvalues. So complex eigenvalues. So this the whole part above the parabola here, complex eigenvalues. Now let's characterize what will happen in each of these spots in here. So everything above the parabola, complex eigenvalues. Now what does it mean if the trace is negative? Well, that means the sum of the eigenvalues will be negative, which means that when you're adding a conjugate pair of these eigenvalues, you get a negative result. Now when you add a conjugate pair, the imaginary parts disappear, and so the real parts will add up, will just be doubled and equals a negative number, and that means that the real part is negative, which means we have a spiral sink. Now if the trace is 0, then that means we have a center, because that means that the real part is just 0. And then over here, if the trace is positive, we're going to have a spiral source. So the trace being positive indicates a indicates that the real parts must be positive, for when you add them together, their complex parts would just cancel away. Okay, now below the parabola is where we get all of the situations where we have two distinct real eigenvalues. So what's it going to mean if we have two distinct real eigenvalues and the determinant is positive and the trace is also positive? That would be quadrant 1, but below the parabola. So what that means is we have two numbers multiplied together to make a positive, so they have to have the same sign, both, so they're both going to be positive or negative, and since the trace is positive, that means the sum is positive, and that means they're both positive. So this means so over here, this means a source. So it's just like a nodal source, just a point source. Okay, we'll ignore the zeros for that for a second. Now let's look down here. So this represents negative value of determinant and positive value of trace. So that means they multiply together to make a negative, so they have opposite signs, and that means then a saddle point. And that'll also be the case over here. Now, if the trace is equal to 0, then we've got a super saddle point where they just are actually of equal magnitude. But so that's what would be over here, and over here we just have a sink. For the same reason that we had a source over here, we have a determinant in this case that is positive, so therefore the two eigenvalues must have the same sign, but since their trace is negative, that means that sign must be negative. And then here what we have is again a repeated eigenvalue, but because the trace is positive, that means it must be positive, and so we have an improper source. And along this one, we have, by the same token, an improper sink. So these represent all of the scenarios we've discussed. And if you ever wanted to know like what we would expect from a certain matrix, even just a sort of randomly chosen matrix, we could just classify it according to this. So just as an example, just a very quick example, classify. Let's just say x prime equals ax, where A equals just any old matrix 1, 2, 3, 4. Doesn't have to be anything very fancy, doesn't have to be anything that works out very cleanly. We can just quickly figure out what the trace and determinant are, and we can figure out then what the result will be. So trace is 1 plus 4 equals 5. Determinant equals 1 times 4 minus 6 is equal to negative 6. So TD equals 5 negative 6, and that puts us down here, so it's a saddle point. Nothing very hard about that. The only hard thing is if it's in one of the top two quadrants, whether it is above or below the parabola, and you can just quickly crunch the numbers with the t and d in question and determine that. But it's not too complicated. The complicated part is figuring out the consequences for each of the quadrants and their position relative to the parabola. But once you figure that out, it's just basically a lookup table. Now let's undertake a more interesting example, something from the realm of physics. So example. So this is oscillators. Okay. So what we are going to do is look at a spring, a spring with a mass on the end. So this is a spring. A spring system, and the spring system in question here is going to have a few parts. So one thing we're going to assume is that we have obviously a spring. And then we have a mass on the end of it, mass m. And then what we'll assume here is that there will also be what's called a dashpot, which is actually just going to be our catch-all representation of everything that is kind of related to friction in the system. So this is the spring, and we'll say it has a spring constant. K. This is a mass, and this represents a dashpot, which is, in other words, just a device that represents friction, i.e., friction. So we're just basically going to personalize the friction in this little device here, and say that right there some of the energy is getting lost into this little dashpot. And furthermore, let's say that if this is the equilibrium spring position, and here by equilibrium we just mean where the spring would be most comfortable, then x would be the distance away from that. So how far it's distended outside of its equilibrium. Okay, well then, the equation that basically relates the position of the mass with everything else will all rely on Hooke's law. Hooke's law. So this is without the dashpot. Force is equal to negative kx. And what force here means is the force required to extend a spring beyond its equilibrium is going to then be proportional to how far beyond its equilibrium you're stretching it. And that constant of proportionality is what the spring constant refers to. So then, by Newton's second law, force equals mass times acceleration, but then that means that force is equal to mass times the second derivative of x, which we can write in physics notation, since this is a physics related problem with just two dots. And so then that gives us m x dot dot, so second derivative is equal to negative kx by Hooke's law. But then if we include the dashpot, i.e. friction, then what we can do is basically assume the friction is proportional to the velocity. And so what we're going to have is the force is going to be equal to negative kx minus c x dot. So this is the constant of proportionality, and x dot will just be the velocity. So then x dot dot plus c x dot plus kx equals 0. So this will be our equation that we will constantly revert to whenever we are talking about this scenario, and it's very related to another scenario as well, or as we might find it more convenient, x dot dot plus c over m x dot plus k over m times x equals 0. So this is what we'll call the spring equation. And what we will now do is figure out, first off, how to convert this into a system of equations, and then we'll figure out what we can figure out based on the relative values of c and m and k. So then, let's convert this. Convert this to a system. All right. Well, we have a set pattern for this. We'll just say x1 just equals x, and we'll say that the derivative of x is equal to x2. So in other words, x1 prime. And then also, here we'll put this in both forms, x dot dot equal to negative c over m x dot k over m x. And so then x dot dot would equal x2, the derivative of that, but that's equal, as known to us, to be negative c over m x dot plus k over m x. And now when we try to just convert the whole thing to our new system of equations, we'll just get negative c over m x2 plus k over m x1. So our system now looks like x1 dot equals x2, x1 prime, I guess we'll write it so that we're now fully in the language of this class. X2 prime is equal to k over m x1. Sorry, this is supposed to be minus. Sorry. You go long enough on these things and you're bound to start dropping your negatives. So it's negative, and then this one is c over m x2. Okay. So some negatives were dropped along the way, but they've been found again. And so then the matrix A that represents this system would be 0, 1, negative k over m, and then negative c over m, which means that T is equal to negative c over m, and D is equal to the determinant, which is going to be just k over m. And now let's try to assign some specific values to these letters and look at various scenarios. So now some specific values. Alright, well let's just say we're going to lock it in at k, so the spring constant, and the mass we will fix once and for all, and then we'll change the coefficient of the dashpot / friction as we go. So k will be 50, and here we're going to use the metric units newtons per meter, because it represents force that it requires to extend the spring by so many meters. The mass, we'll just say, is equal to 1/2 of a kilogram. Alright, so scenario A, let's set C equal to 0, and for the record the units here would be newtons per meter per second, or in other words newtons seconds per meter. And so this represents the case of undamped oscillation. So it has not been damped at all. There is no friction. We just have a spring. The spring has been set in motion, perhaps, depending on the initial conditions, and it'll just be oscillating back and forth. So I think we all know in our mind what we expect this situation to look like. It'll be going like that. But let's see if the math backs us up. Alright, well, t equals then -0 over m, which is 0. d is equal to k over m, which is 50 divided by 1/2, which is 100. And so we're talking about a place that is, remember this is the d and this is the t, so this is going to be a center. So it's a center. So in other words, if we were to look at a graph of the motion here on the phase plane, here, let me just try it again. So in the phase plane, if this one is the x prime, or in other words just the x, and this is just the x dot, and this one is the x, then we would be seeing just something that was going around and around and around in a circle, and where exactly it was in its circle, that would be, and whether it was going clockwise or counterclockwise, that would totally be something that the initial conditions would have to, initial conditions and the specifics of the numbers would have to determine for us. But essentially, we just have something that's going around like this. And that would mean then, if we're tracking the x over time, so x graphed over t, we would be seeing x being positive, 0, negative, positive, 0, negative, and it would just be oscillating around in a completely sinusoidal way. So this is just an undamped harmonic oscillator. And if we wanted the actual equation for x, we are perfectly capable of finding it. We have all the numbers we would need to fill out A, and we could in fact find it with the tools that we have in our arsenal. All right, so B. So this case was easy to classify. Let's look at the next situation, where we are going to take a value for C that is equal to 5. Alright, so let's think about this. So if C equals 5, then T, which was equal to negative C over M, is going to be negative 5 over 1/2, which is equal to negative 10. Alright, as for D, that's equal to, that's just going to equal 100 in all of these, really, because the mass and the spring constant aren't changing here. So we have D equals 100, T equals negative 10. Now here, if we weren't sure where it was relative to the parabola here, we can just figure out, is D greater than 1/4 t squared, less than 1/4 t squared, or what? So here we can see that if we did t squared, that'd be 100, a quarter of that. So that means that D is going to be greater than, so we're over here somewhere. So our D is greater than 1/4 t squared. So that puts us over here, which is a spiral sink. So what does that mean then? That means if we look at x bar or x dot versus just x, because that after all is the two variables we have in play. And if we look at, so we have a spiraling inward situation like this. And then if we, if we look at just x versus t, what we would be seeing here is it oscillating going through oscillatory motions of less and less and less amplitude. So it oscillates with decreasing amplitude, and this situation is called underdamped. So the spring is underdamped. Okay, now let's look at the case of a third value here, and in particular, now let's take C equals 10, and these are Newton seconds per meter again. And so now what's T going to equal? So T is going to equal C over M, negative that. So that's going to be equal to negative, so it's going to be equal to negative 20. D is going to still equal 100, as it always has. And now, if I look at the situation here, so 1/4 t squared is actually going to be 1/4 times 400, which equals 100. So that means we are exactly on the parabola. And that means that we have a sink. We have a sink, and it's the sink that almost spirals, but doesn't quite. So this is the case of a repeated eigenvalue. So we get a nearly spiraling sink here. So let's say whatever, and this is all just speculative, where the actual eigenvectors were, but essentially here what we can just say is it was something like and so what we get when we do the x versus t is we get something that is almost oscillating so it almost oscillates, and here this is almost a spiral, and this is what is called being critically damped. So it's critically damped. So this is what is called the threshold case, or the bifurcation, where the situation assumes the kind of borderline character. And then D here, we'll take a C that is just a little bigger still, 15 Newton seconds per meter. And so our trace is now going to equal negative 15 over 1/2, which is equal to negative 30. Our D is still fixed at 100. And so now what we have is a situation where we are below the parabola. Our trace just keeps getting pushed further and further left. Our determinant keeps on being the same. And so we're over here, and that means we are just purely a sink, and it's not. So this is not a case of a nearly spiral. This is a case of something that looks kind of like this. And again, it's all very speculative. We haven't gone through the actual work of finding out what these vectors would be. But we have some vector going one direction, some vector going another direction. Let's say this is, sorry, by habit, it's easy to draw them going out. So then you just have something that, let's say this one is the dominant one. So then you just have something that is starting off going kind of this way, and then comes in. So they're just coming in this way. So what this means is basically we've got too much friction for this to oscillate. So then what happens is if we follow the path of one of these x's, it's just going straight down to 0, no oscillation. So it doesn't oscillate. It just exponentially decays down towards 0. So this is a case of an overdamped spring. So those are the cases. Undamped, which just is freely oscillating back and forth. Damped, but not enough to actually suspend the oscillation. So in other words, underdamped. Then there's the critical point, the point right in between, which is neither here nor there. It almost oscillates but doesn't quite, and that's critically damped. It goes through kind of one half-hearted oscillation and then it gives up. And then there's critically damped, where the spring constant and the friction are such that what basically happens is the friction just smothers all attempt at oscillation. So this one's like a slinky. It just is stopped in its tracks. So otherwise, the other ones, they recoil somewhat, or they recoil a lot. This one, it just goes straight down. Alright, so now let's go over to Bluffton to get a view of these things just to see what they generally look like. Alright, now let's have a look at the actual phase portraits for this system. We were able to speculate, but now let's get it for sure. So we'll go to our favorite phase portrait producing applet, which is the Bluffton, and we will put in here the specifics of each of our examples here. So on the first one, we have, so let's see. So these are as good of variables as any. So let's see. For the first one, we have 0x plus 1y. So that's just going to be y. And on the second one, we're going to have negative k over m. In other words, the determinant, like negative determinant. And then we're going to have negative c over m, which is the trace. So for example, A, the determinant was 100, so it's going to be negative 100x, and then the trace was 0, so that'll be all. Let's clear away this unnecessary thing, and let's see what we get here. Oh, there it is. Okay, so here we have our center, and we can see. All right, so sketching these curves might be a bit dicey. Let's go ahead and change our window just a little bit in order to produce something a little bit better here. And in particular, the problem here is that the y, we've got such a high value for this that it's really affecting the velocity here. So let's see, so we can make it a little bit more reasonable, and it's still producing something which should not be. There it goes. Okay, if you make the step size small enough, then you can get it to be appropriately centered. And in particular here, now we can see a little bit better. Maybe if we make this negative 7 to 7, then we'll have the best looking. That's pretty nice. Pretty nice. Okay. And in particular, let's put in, just for the sake of it, well, this is a fine initial condition, 0, 1. So this would represent the spring initially distended by 1 unit and then let go. Now, if we look at the time plots, so sure enough, this does appear to be a center. Now, if we look at the time plots, we see this, and let's actually zoom in a bit on it, and we'll lock t equals 0 on the left. So you can see what we get is classic oscillation. And remember, y was a constructed variable. It is not really of any relevance to us. All we care about in reality is the x. So the x is the one that actually is of some actual meaning. Oh, I'm sorry, let me change this initial condition 1, 0. So I wanted to change this. So this represents it being distended by 1 meter to begin with and then released. So the red one here is the only one that actually matters. The blue one we can also see is zigzagging back and forth. And we can see that, that in particular, thanks to how high this value is, the velocity of this is a lot more, it have a lot higher amplitude in its oscillations than the actual position. All right, well, in any case, it is doing that which we hoped it would do, which is be a center. And that produced a time plot that was oscillatory. Okay, good. Now, so this was example A. Now let's take a look at example B. So pretty much the same thing. It's just the matrix that we would make would end up having a, so essentially we get the trace in the bottom right corner. And so this is going to be minus 10y is going to be the only important change here. So hit enter and see what happens. Okay, so here now we have the spiral sink. So it is we can see now that it is clearly spiraling inward in a sink-like fashion. Now, if we look at what the actual solution curves look like, we have oscillations that then quickly so the oscillations they dampen more quickly than I gave them credit for, and that's because we do have essentially an exponential decay in our amplitude. So you can see it's already pretty much done oscillating even after just like 1 second, but that's because we have such extreme numbers here, which lead to exponential decay functions of rather extreme nature. So it does spiral in. As we can see that we didn't portray it extremely accurately in the number of oscillations it was going to do before they became too small to see, but close enough. All right, now let's put in case 3 where we had the critically damped system. So now you see it doesn't spiral, but boy, does it want to. My diagram did not accurately represent the actual orientation of these curves, but remember, it was purely speculative. The important thing was that it's these nearly spiral solution curves that we've seen when we have these repeated eigenvalue solutions. And in any case, what we see is it just goes down. It wanted to oscillate. It wanted so badly to oscillate, but it was just barely smothered in its oscillations by the dampening. And then finally here, the last case of full-on over-damped system. Let's clear all the curves and submit just this one. So it doesn't do anything approaching an oscillation. It just straight up decays. So it just straight up decays right on down to 0. Now, so the moral of this is that we were correct in the vague picture, but we were not necessarily correct in the specifics. If you wanted the more specific nature of the solutions, you would actually have to roll up your sleeves and solve. And in order to solve them, we have the techniques that are necessary. If you have the matrix, then you can find the eigenvalues. You can find the eigenvectors. You can find the two components of the solution, and you can actually then explore those. So these could be solved analytically with the tools that we have. And in fact, so I'm going to cut to the chase on this one. But in fact, I have solved them, and I've created a little Desmos animation to show you what happens to the spring in each case. So this little dot represents the bob on the spring, and this first one is case A, where it is not damped at all. So let's just watch for over the period of 2 seconds what happens to the mass on the spring. So you'll notice it is just oscillating back and forth in the style that we would expect from something that has no dampening factor whatsoever. So starting at so I gave this one initial conditions of 2 meters, and then just let it go back and forth from there. So that represents the situation of the completely undamped motion. Now we will dampen it. So this is formula B as I've constructed. I'm not showing you these formulas because I want you to do that as part of your problem set. So I'm hiding them from you, but I'm just showing you what they will generally do. So with B, we have friction, not enough to completely prevent any oscillation, but quite a bit. So what happens is it oscillates slightly, and then after that, the actual oscillations become too small to see. So it's technically still oscillating, but it becomes too small to see. And now it just reset. So what we have here is something, we stretch it out, and then it kind of jiggles back into place. Okay. Then example C, this one is critically damped, So what happens is it wishes it could oscillate. It wants so badly to oscillate, but then it doesn't actually manage to recoil back. It wanted to oscillate. Notice, almost, but it just barely won't. It's right on the brink of being springy, but instead it was too dampened. And then the final one here is D, which is the overdamped case. Here, it was stretched out of joint and it just returned itself back to where it belonged. So it just was stretched and it just kind of unstretches. You don't see any hint of oscillation whatsoever. Okay, and now let's go back to the fully oscillatory one. This is the one that's just doing what a spring does, just going back and forth and back and forth. And this one represents just full undamped oscillation. Okay, well, that's just a little demonstration of the behaviors of these different solutions. What I did was I created functions for each of the solutions. Like I actually solved them secretly on my own. I found formulas for the x, and then I put those into Desmos, and then I created this with a slider of p for parameter, because t is not very helpful, since Desmos considers that to just be the parametric form of an equation. And then I just let it get animated from 0 to 2 seconds. So if you want to try, you have the equations in question. You can make the systems, you can solve them, and you can find the functions and try to see if you can reproduce these animations. But they just spring. This one was dampened oscillations, and they dampened pretty quickly because the numbers here were pretty big. And then right on the brink, almost oscillates. Like notice, oh, it looks like it might come back a little bit, but nope. And then finally, no oscillation at all. It was stretched out, and now it unstretches. Okay, so those are the possibilities for what we can see, and we can categorize them all based on their position on the phase plane, for example. Or sorry, on the trace determinant plane. Okay, well, that'll do it for this episode of Math 256. Join me next time, where we start delving into new material in Chapter 4. All right, until then, bye.